types of chemical reactions in the topic of stoichiometry, okay? I have the lights off because I want to do my simple demo with magnesium and oxygen reacting. You've seen this reaction, do this reaction before, but it's one of my go-to reactions to explain a lot of different concepts. It's simple, it's quick, and it's easy to analyze. So I love it, okay? No problem. So, when you're looking at types of chemical reactions. Okay. All right, so no problem. So, here we go. You have a flame right here, okay? And as always, I should be wearing goggles. You should be wearing goggles in lab, but I'm taking an exception today. I have a magnesium ribbon right here. You've probably seen before. Probably hard to see. Here you go. All right, the magnesium is an element, right? And what we're simply going to do, guys, we are going to react this element, magnesium, right, with the other element that we're not seeing right now, oxygen in the air that we breathe, yes? Okay, so here it goes. We place it in the flame. All right, you see that? Okay, all righty. Once again, the ash that's on the ground, okay, is magnesium oxide. So once again, guys, all right, the element magnesium reacting with the element oxygen in the air, producing magnesium oxide. All righty. So let me take this flame off. Let me go turn the lights on. I'll be back. Okay, so what did we just do? We have magnesium, right guys? Okay, Mg, and we're reacting with O2. Alrighty, so when Mg reacts with O2, we get, okay, MgO. Alrighty, okay? Now, what type of reaction is this? This type of reaction is called a synthesis. A synthesis reaction. And how do you recognize it? How do you recognize a synthesis reaction? Okay, it's always more than one substance. Okay, it's always more than one substance producing a compound. Okay, it's always more than one substance producing a compound. So it's two or more things coming together to give you a compound. In this case, the element magnesium is reacting with the element oxygen to produce the compound magnesium oxide. All right. Our next reaction that we're going to do, okay, will be the opposite of synthesis. All righty. So let's look at that. Number 2. We'll name it afterwards. So let's set it up. All right, bam. That's my graduate cylinder. This is hydrogen peroxide. Okay, 30%. Okay. This is potassium iodide. It's going to act as a catalyst. And we know from experience and from living environment and so on that a catalyst speeds up reactions for us, right? But we're going to learn a little more about catalysts later on in the topic of kinetics and equilibrium and so on, what it does and so on. Okay, no problem. Okay, alrighty. And I have some dish soap right here. Now, what's the principle that's going to happen? We are going to place this hydrogen peroxide into our graduate cylinder, alrighty, and then we're going to add potassium iodide. But before we add the potassium iodide, I'm going to put some dish soap inside of the hydrogen peroxide. Now, the reason I'm doing that is what's going to be given off is water, okay, and oxygen. Now, the dish soap is going to trap the oxygen, okay, while it's being given off, and hopefully we see a nice foamy evolution coming out right here, okay? No problem. So, here we go. See that? That's my hydrogen peroxide in there. Okay. Now we don't want to forget to put my dish soap in. Good amount. Bam. I get the swirl. My students from last term, you saw me do this in class. You know, no problem. I love this reaction too. Okay. Alrighty. Now, what I'm gonna do? Got a beaker. My potassium iodide. Got my scoopula. I'm gonna put some in the beaker, and I'm gonna make it aqueous. All right. You can put it in a solid, but I find when you put it in as an aqueous solution, it makes it a bit more, better in terms of the rate of reaction. Okay, got my water. Okay, give it a little stir. Okay, so once again, what are we doing, folks? We're starting with hydrogen peroxide, right? And we're gonna add it. We're gonna add this guy to it, potassium iodide. Potassium iodide is our catalyst. It's breaking down as we speak, right? But very, very slowly. What we want to do, we want to speed the reaction up and see, the products. Okay? So, let me hold this like this. Stand back. Okay. Can you guys see? All right. There we go. See that? See that? See that? Okay. Now we're going over here. Oh man. Let me switch this around, see if you guys can see. There we go. Okay, so that's our reaction there, folks. That's our it's called the elephant toothpaste reaction. It's pretty cool. Alrighty. Notice the gas that's trapped inside of the dish soap. Also notice there's some, I don't know if you can see or not, right? But some fumes being given out. This reaction is pretty exothermic, guys, all right? So here we go, okay? That's our hydrogen peroxide breaking down to produce water and oxygen. Okay, that's our second reaction. So does anyone know the name of that reaction? It's the opposite of synthesis. It has a couple of names. Okay. So the opposite of synthesis, okay, is called decomposition. Okay, decomposition. Synthesis has another name, it's called combination, and decomposition has another name, it's called analysis, right? But typically, Regents level, we tend to use synthesis and decomposition. Now, we know from our regular language, right, that decomposition means to break down, yes? Okay, and that's essentially what's happening. You're starting, right, with one substance. In this case, it's H2O2, hydrogen peroxide, and you're breaking down into two things. Okay, more than one substance. You're breaking down into water, H2O, and oxygen, O2, okay? Now, ladies and gentlemen, these equations right here, they're not balanced, okay? So what we're gonna learn about that later on in terms of how you balance chemical equations, all right? Because that's another topic we're gonna do in the future in topic of stoichiometry. So I'm just leaving these guys unbalanced, and later on we'll balance them. My main goal today is just to talk about the types of chemical reactions that you need to know. Alrighty. Okay, so for this particular decomposition, how do you recognize it? You have one substance, okay, one substance on the reactant side. Okay, one substance on the reactant side. Always start with one substance on the reactant side. Got to be a compound, right? And what happens? You break down into two or more substances, okay? So one substance, okay, producing, alrighty, two or more substances. Okay, bam. All right, so that's synthesis one, decomposition two. Okay, let's go to the third reaction, number 3. Okay, so 1 molar, it's pretty strong. All right, bam. Now don't worry, guys. You're gonna learn about concentrations later on this term. So don't, molarity. You can learn about that later on. You probably heard the term already, but no problem. Okay. I have some magnesium metal turnings here. Okay. I have a balloon. Alrighty. Okay. And I have a Erlenmeyer flask. You guys a better view. Alright. Okay. So my acid, my magnesium, my balloon, and my Erlenmeyer flask. Alright. So what I'm going to do, I'm going to scoop some of this magnesium, right? I'm going to put it inside of the balloon. Okay. Let's see if I can do this. Oh, goodness. Let me get another balloon. That one doesn't want to cooperate. Okay. Okay. There you go. Some more. There you go. I think I'll do one more to make sure I get Mg inside. So once again, I use Mg in the first reaction. I'm using magnesium again. So magnesium is pretty cool. All right. There's a nice level of reactivity to it. It's not overly reactive, but it's decently reactive. Okay? Alrighty. So my next step is I'm going to put some acid in some of my Erlenmeyer flask. Alright? It's going up. Bam. And bam. Okay. I think I'm going to put a tiny bit of water inside of this 1 molar. Right? Okay. Now this reaction, sometimes it works right away and sometimes it takes a little while to work, but I'm going to leave it right here, okay, with the balloon to see what happens over the course of time. Okay? Alright. So, this is our Erlenmeyer flask. Okay, with the acid in it, right here. This is our balloon, okay, with our magnesium turnings. What we're gonna do, okay, place it on there. Got it? Okay. And bam. Here you go. Oh, that was nice and immediate. Okay, so this reaction right here, you have magnesium reacting, okay, with the hydrochloric acid, and it's producing hydrogen gas, okay, and magnesium chloride, okay, no problem. So let's go over here and analyze that. It's pretty cool. Nice evolution of hydrogen gas right there, okay, alrighty. Now back in the days, I used to actually take a flame, right, light the balloon and get a nice little explosion, right, but I'm erring to the side of caution as in my later years. Okay, so yeah. Okay, so number 3, we have magnesium reacting with, okay, can you guys see that? HCl, okay, producing MgCl2 and hydrogen gas. Okay, alrighty. So what's happening here? We have an element, okay, and now what the element is doing is reacting with a compound to produce what? To produce another element and another compound. Different element, different compound. So this particular element, Mg right here, is replacing the hydrogen, okay? Think of it as kicking it off, okay? And the hydrogen now is by itself. So this reaction is called a single replacement reaction, Okay, now sometimes it's called single displacement, no problem, either or no problem. But how do you recognize it? An element reacting with a compound to produce a different compound and a different element. And you notice, right, it's always positive replacing positive, okay, or negative replacing negative. Or think of it like this, metal replacing metal and non-metal replacing non-metal. But H in this case here is positive, and magnesium forms a positive ion. So that's what I mean by positive replacing positive, okay? That's single replacement. I'll make a note here. Element replacing another element, okay, in a compound. That's called single replacement. All right, so let's do another reaction. Ooh, nice and very nice. Okay, so that's our single replacement right there. Okay. Okay. Here I have, here I have a beaker and my test tube. Alrighty. I have here lead nitrate, our good friend potassium iodide. So what we're going to do, we're going to react our lead nitrate and our potassium iodide. We got two compounds this time. Just before we had elements in a compound, but now we have two compounds. We're going to react them and see what happens. Okay? No problem. So, a scupula for my lead nitrate. Alrighty. And I'm going to put a small amount inside the test tube. Okay? I'm not going to use a lot of material in this particular reaction. Alrighty, so here we go. That's our lead, right? Okay, I'm going to make it aqueous, but not, not very aqueous. There we go. I'll put a tiny amount of water in there. I'm going to stir it up. Okay. So that's our lead nitrate aqueous guy right here. Okay, I'm gonna put it over here. Now what I'm gonna do, I have some potassium iodide right here that we used before that acted as a catalyst in the decomposition reaction with hydrogen peroxide. But this time, I'm gonna use it as an actual reactant, okay? So it's not acting as a catalyst anymore. All right, so what I'm gonna do, I'm gonna put a few pieces, okay, into my aqueous lead nitrate, and we'll see what happens. Okay. You guys see that? Originally it was clear and colorless. Added the potassium iodide, bam. Okay, we have a yellow substance being formed there. Now we're going to learn the term precipitate, right? That yellow stuff that's formed now is called a precipitate. Okay, no problem. You can actually, filter this and separate it out, no problem. So let's analyze what type of reaction is this. Okay? Alrighty. So, what do we do for number 4? Okay. We had lead nitrate, okay, PbNO3, subscript 2, and we added potassium iodide, Ki. Alrighty? No problem. Now, in this particular reaction, guys, potassium is replacing the lead is taking the place of the potassium. There is a double switch, okay? In the previous reaction, we had a single switch, okay? So the magnesium just replaced the H, and that was it. But in this place right here, okay, you have the K replacing the Pb, and the Pb replacing the K, all right? So the metals are switching places, right? So you would expect the K to link up now with the NO3. So what's going to happen, you'll get KNO3. Now guys, remember we did naming and crisscross with ionic compounds? Be very careful. K is +1, NO3 is -1. You should always, do the crisscross method and check to make sure you have the right compound, all right? Okay, now when the Pb replaces the K, the Pb and I will form compound PbI2. I know that because in this particular case, the lead has a +2 oxidation state, okay? Now, I said before, I'm not balancing. We'll learn balancing later on, no problem. But the main thing we want to write down, folks, this type of reaction right here, where you have a compound reacting with another compound, normally there will be ionic to give you two different ionic compounds. That's called double replacement, okay? So this is called double replacement, okay? And you can basically say two, okay, compounds reacting, okay, to give two different compounds. You see that? Yep. Okay, no problem. So that's that. All right. We have one more reaction to do. All right. And this one right here, I'm not really going to do a demo per se. I'm just going to talk about it. Now, guys, you saw me at the beginning of the video, right? That I used the burner, right? Now, every time, guys, let's say you have a gas stove and you put it on or you put the key in ignition. Every time you do that, you successfully did a combustion reaction, okay? Now, there's a bit of controversy about combustion reactions, right? Some teachers say, well, as long as it produces oxides, it's combustion reaction. I'm going to use the Regents definition, okay? We'll sort out the controversy later on. Now, combustion reaction is a reaction where you have a substance reacting with oxygen, right, O2, and it produces CO2 and H2O. Now, in your gas stoves, right, they tend to use methane, CH4, okay? But there's a wide variety of hydrocarbons, okay, that can be used. You can use ethanol, for example, or alcohols. Alcohol can actually run cars because the reaction is pretty exothermic and so on. Okay, so there's a wide variety of things you can use to, okay, cause a combustion reaction. There's octane that you know from the gas station, all right? There's, for example, this guy right here, propane. Now, guys, we're going to learn the names of hydrocarbons in a topic called organic chemistry later on, right? So don't you guys panic with the names, okay? But just know, how do you recognize combustion? Okay, substance reacting, okay, as you're running down with oxygen, O2 for short, to produce CO2 and H2O. Okay, it's a classic combustion reaction. Alrighty? Alright, guys, as always, hard work with sacrifice equals success. Study hard, be well, take care.